Hi, I'm Antonio Sala. In this video, we are going to discuss the intuition on the Matérn kernel and the squared exponential limit case from a control engineering or signal processing point of view, in the sense that, okay, if we look at the Wikipedia page on the Matérn covariance kernel, here we have it. So it says that it's used in machine learning, image, geostatistics, whatever. And here we have covariance kernel definition given the distance between points. This thing has three parameters, nu, rho, and sigma, and it involves the gamma functions, modified Bessel functions of the second kind, and understanding this seems kind of difficult. What are those Gamma and Bessel functions and that stuff? These sound Chinese to me, and I don't speak Chinese. So, what's the goal of this video? Well, it's understanding that this Matérn stuff is just like filtering by, say, transfer functions with a repeated real pole. If I have white noise entering this filter, which we will call spectral factor, then if I have samples of the output, I will interpolate them with Gaussian process regression formula using Matérn kernel. I mean, this is the basic idea, and understanding it by example, no proofs, checking the results from Matlab simulations is the main goal of this video. Let's go. As I said, the idea is that these parameters, nu, rho, sigma, whatever in Wikipedia, will be related to the amplitude A, time constant tau, and order of the multiple real pole filter associated to this Gaussian process we are describing. We will need some corrections in order to find a nice limit case, which will be the squared exponential kernel, in the sense that, okay, let us first draw the Bode diagram, frequency response, of these things, fixing A and tau and increasing n. So we'll see this code in which, well, I will have 5 different values of filter order, 1, 2, 3, 6, and 15, and I will plot the Bode diagram of this. Then here we have the Bode diagrams, and well, if we increase the order, let's say I put 30 in the last element, we filter more and more. So if we keep the time constant and amplitude of the filter independent of the order, we filter, and at the end, in a limit case, we would have nothing at the output. This tends to 0. But from an engineering point of view, this is okay in the sense that we are not going to use an infinite order filter. So if we decide, let's say, to think in a 4th order filter, we can later on choose time constants, amplitude, whatever, to mimic some variance, power spectral density, whatever. But the theory wishes to have a limit in a certain sense. So the theory underlying this formula proposes making the filter faster as the order of the filter increases in order to converge to a non-zero limiting behavior. The time constant increases with the square root of the order. So if I start with a filter with time constant 1, first order, let's say, then the mathematicians would tell me that if you don't think that your high frequency filtering is good enough, but you want to keep your low frequency components more or less as they are, then increase the order from 1 to 2 and decrease the time constant. The time constant gets divided by something related to the square root of the order. And if you are not happy, increase to 3rd order and decrease the time constant, and so on. So in this way, you will have a limiting behavior in which more or less you keep the low frequency passband of this filter, but you increase the selectivity and the slope at high frequency of the attenuation is larger. So if we do this, then instead of having this stuff that ends up washing out everything in zero, this new sequence of filters has more or less, let's say, the same cutoff frequency around here, let's say the 6 decibel stuff, for instance, but has increased selectivity, increased slope. And the limit case is a famous one. It is the exponential quadratic in frequency, also in time, because this thing is its own Fourier transform, more on that later, but you know, the bow diagram of the exponential of minus frequency squared is the limit case of this sequence of filters with this cutoff frequency. So this is the intuition and the motivation for the squared exponential kernel. It is not the Gaussian process stuff. This formula arises from no Gaussian at all. It arises from the limit case of this sequence of more and more and more selective filters until the squared exponential, you know, ends up with an infinitely vertical, let's say, slope, whereas the finite order filters end up in the bow diagram with just a constant slope, a straight line, with 20 decibels per decade decrease times the filter order. But the exponential is infinite. So we see that order 30 and order 30 millions are already close. The transfer function of the filter is the square root of the power spectral density, so power spectral density would be just multiplying by 2 the decibel axis. The transfer function of the filter is called the spectral factor, but the covariance and statistical analysis is done with the square of the modulus of that, which is the power spectral density. So this is the intuition of this kind of filter. And now the other modification is the fact that as we are cutting more and more and more of the high frequency, the output variance of this filter noise would decrease, and then we need another modification so that we increase a little bit the gain to keep the final variance constant, sort of normalizing divided by the 2 norm, the standard deviation of the output to white noise. So the true sequence of filters underpinning these derivations is this one. We increase slope, we increase gain, and we get to the limit squared exponential filter. And all these filters have the same output variance, but with a sort of waterbed effect, in the sense that if I shave more and more the high frequency components, then I move them to the low frequency bands, increasing the DC gain. So, with these interpretations, now let us try to recover this formula for the Matérn covariance, whatever, and the spectral density in Wikipedia. So, we will analyze this finite order filter 3 over s plus 1 to the 10th power, 10 poles s equal minus 1, and then this thing will be the spectral factor, and the power density will be the square of the modulus. So the square of the modulus of a complex number can also be expressed as the product of it times its conjugate, and that's what we are doing here. And so the power spectral density ends up being this formula. I mean, the modulus of 1 plus j omega will be a square root of 1 plus omega squared, and the square of it is 1 plus omega squared to the 10th power. And then the covariance is the inverse Fourier transform of the power spectral density. We get this expression, which is, wow, I'm very happy that Matlab knows how to do it, because, you know, this Bessel function stuff is kind of complicated, but it is a polynomial times exponential. And if I type these Gamma and Bessel and whatever functions with these values for the nu and rho parameter, you can pause, download the code, and check that this is what Wikipedia is saying here, then okay, if I evaluate this with these nu and rho parameters, then I get this kk2, which is exactly the same as above, x9, 45, x8. Here we have x9. It has absolute value because it must be symmetric on the abscissa axis. And this formula here, just assume that x is positive. What is x9, 45, x8, etc. Same as here, we will plot together and they will just be copies of one another. And then if we wish to delve a bit further on this power spectral density and covariance, we can recall that the integral of the power spectral density is the Gaussian process steady-state variance. We have some 2 pi here stuff because of alternate definitions of the Fourier transform, frequency in hertz versus radians and things like that. No problem, it's just scaling. But the integral of the power spectral density ends up evaluating to 0.91, which is the 2 norm of the spectral factor of the filter we are assuming that generates the Gaussian process. And of course, if I substitute a time separation of 0 in the covariance, then I get again. So from spectral factor power density and inverse transform, we get the covariance function, and indeed we check without proof, of course, that it coincides with this Gamma and Bessel formula stuff. And the limit case is this squared exponential kernel. This is in time, in x, in abscissa, whose Fourier transform is the same function. I divide here by 2 just because it's the square root, but its power spectral density is this squared exponential in frequency, this both diagram stuff. And if we see it in time domain, in inverse Fourier of the power spectral density, then here we have in yellow the squared exponential kernel, which has nothing to do with normal distribution, remember, it's just the inverse Fourier of a given both diagram. And we have the finite order covariances from my inverse Fourier in blue and from Wikipedia's Bessel formula in red. And of course they are coincident and almost coincident with the limit infinite order squared exponential. Of course, if I do it with a lower order, say 4, then this 4th order filter of a noise generates this time or spatial distance covariance kernel, coincident again with the Bessel formula stuff, and in this case departs a little bit away from the limit infinite order squared exponential. But as really covariance kernels in priors is something that we usually invent when setting up Gaussian processes, which is the practical difference between the red or blue lines with Bessel functions and the gamma and the like, and the difference with the yellow one, well, maybe it's not that much in practical terms, so that's why in many examples people forget about this strange formula and sticks to the limit case of the squared exponential, because once you go away from first or second order, let's say, things start getting closer to the exponential. So with this discussion on the relationship between the Matérn kernel and exponential quadratic with filtering a signal with multiple real poles at the same location, we end the video here. Thanks for watching.